Hi, good day. My name is Joshua Emeta, and with my team, Alexis Barron, Travis Kraus, and Emmanuel Akatuba, we worked on the project Landfill Remediation. We're going to start with a problem introduction. As can be seen in the picture at the right, contaminants from an inactive landfill are leaking into the groundwater below the site. Some of the contaminants are reaching nearby streams. And as we're going to see in later slides, the design of various alternatives to determine the most effective solution to reduce contaminated groundwater seeping into nearby surface waters. Alternative A, which would be to do nothing. There is no corrective measures implemented, and as we can see on the picture to the right, a head profile shows steady state conditions. Discharge into the river is 0.1614 cubic feet per second. Alternative B, impermeable cap. Impermeable clay cap covers landfill. Reduces recharge into site, which reduces discharge of contaminated groundwater. As we see in the picture to the right, the head profile shows conditions after 30 years. Discharge into river is 0.1274 cubic feet per second. CAP achieves a leakage reduction of 21.1%, but it is not substantial enough to reduce worries of contamination. Alternative C, cap and confining wall. The confining wall reduces the discharge of contaminated groundwater. As we can see in the picture to the right, head profile shows conditions after 30 years. Discharge into the river is 0.0288 cubic feet per second. The cap and wall are an improvement and preferred over the cap alone, because there is a leakage reduction of 82.2%. Alternative D, cap, slurry wall, and drain. The slurry wall and drain are located around the perimeter of the landfill. Drain carries away discharge, and as we can see to the picture to the right, head profile shows conditions after 30 years. The discharge into river is 0.0147 cubic feet per second. Now, the addition of the drain improves on the previous alternatives because there is a reduction in river leakage of 90.1%. This is the highest thus far. Alternative E, cap, partial wall, and partial drain. The wall and drain are located along half of the perimeter of the landfill. Again, as we see to the picture on the right, head profile shows conditions after 30 years. Discharge into river is 0.00193 cubic feet per second. This alternative has a reduction in river leakage of 98.8%. This is the highest of all the alternatives. Alternative F, cap, well, and partial drain. The drain is located along half of the perimeter of the landfill. Well pumping is at a rate of 1 cubic feet per second. Again, as we see to the picture at the right, the head profile shows conditions after 30 years. Discharge into river is 0.0134 cubic feet per second. This alternative had a reduction in river leakage of 91.7%. For the last alternative, alternative G, Cap and wells. There are two wells pumping at a rate of 1 cubic feet per second. It is located on column 35, rows 30 and 45. As we see to the picture on the right, head profile shows conditions after 30 years. The discharge into the river is 0.0103 cubic feet per second. This alternative has a reduction in river leakage of 93.6%, and because of its cost effectiveness, this is our preferred alternative. Here we have a comparison of all the mass balances of all the alternatives. As we can see, alternative E has the highest reduction of river leakage at 98.8%. To conclude our findings, alternative E, the cap with partial wall and drain, produced the largest decrease in river leakage. Alternative G, the two wells, is the most cost-effective and produces the second largest decrease in river leakage. And also, alternative G is the recommended alternative because it provides minimal construction disturbance to the landfill and still has a 93.6% reduction in leakage reaching the river.